Okay. So right, so I guess I should start. Um, okay, so last lecture we talked about some preliminaries, notation and concepts from probability that are useful if you want to understand the full context of these linear Gaussian graphical models. And well, now I want to actually tell you what the linear Gaussian graphical models are. Um, but maybe I'll just to connect back to what was doing at the end. We talked about Gaussians and hopefully convince you that these are really great. You know, they have all these amazing properties, and one of the properties was that the marginals of a multivariate Gaussian vector are again Gaussian. The conditional densities are again Gaussian, and linear transformation of a Gaussian was a Gaussian again. And I'm just gonna write that last one here. So recall the following: if X is a random vector that's Gaussian, m-dimensional, mu sigma, and here mu was the mean parameter, and sigma has to be a symmetric positive definite matrix, which I'm gonna denote by this PDM. Right? So this is the m by m symmetric positive definite matrices. And well, we had such a Gaussian and this linear map. So it's a transformation K by M, full rank. Then A times X was again Gaussian. But now, well, the dimension now becomes K because I'm multiplying K by M by an M by 1 vector. So this is now a K dimensional multivariate Gaussian with mean A times mu and covariance matrix A sigma A transpose. So this was the last thing we talked about. And well, one of the corollaries of this is that, for example, I mean, I could have taken just m by m invertible, and of course this will be true. But this k by m is actually nice because, for example, let's say that x is just xy, just two-dimensional, and I take A to be the 1, 1. Okay, so just 1 by 2 transformation, then A times X is simply just X plus Y. So what this is telling us is that if you have two univariate Gaussians, X and Y, then X plus Y is again, right? So the sum is again a Gaussian, right? So now this will be now a Gaussian. And well, we know if the originals were mu1 sigma 1 squared, and the second one is mu2 sigma 2 squared, then the sum will be again univariate Gaussian mu1 plus mu2. And then here it's not the sum of the sigma squareds, right? Because we had to look at this, and there is a covariance matrix, right? So here we have sigma 1 squared, sigma 1 2, sigma 1 2, sigma 2 squared, and now we need to find we need to do 1 1 1 1. So we see that we get sigma 1 squared plus 2 sigma 1 2 plus sigma 2 squared. And this shouldn't be a surprise because we already had an equation that says that in general, the variance of a sum is the sum of the variances plus 2 times the covariance of x and y, right? So I mean, these we could already know just from properties of expectation of a sum and variance of a sum. But what we couldn't know immediately was that it's gonna be a Gaussian again. But it is in this case. So just like a nice, another, and in particular, this means any sum of Gaussians, right? If you are, even if you have coefficients, it's still gonna be Gaussian. So this is great. But okay, now really let me define the linear Gaussian graphical models. Okay, so the setup is gonna be G is gonna be a graph. So you can see how graphs are appearing in all of the lectures in a sense, right? So there was one already with Sarah, and now with Thomas, there was also a graph. Now there is a graph here. The graphs are very important for me. So this is gonna be, I'm gonna denote it like B and D. Normally there will be an E for edges. I agree. But here I'm gonna really specify that there are directed edges. So that's why I call it D instead of E. And so V is my vertex set, and it's gonna be finite. Finite vertex set. And well, since it's finite, normally I'm going to be labeling it with the first M natural numbers, positive. So this will be, normally I'm gonna do just M, which in Thomas notation, this was 1 to M. Okay. So this is gonna be V, and D is a subset of edges, right? So this has to be pairs, and the idea is that I comma J is in D, if and only if, well, this represents an edge, directed edge. So this is gonna be, I'm gonna just denote it as really an edge. So I directed to J. Okay. And so maybe right here, directed edge. And in this case, when I is pointing to J, we're gonna say I is a parent of J. So parent. And J is a child of I. Okay. So then we have parents and children. And well, since I already defined this, I'm gonna already define for J in V, we can define the set of parents PAJ to be all the I's in V that are pointing to J. So just the set of all the parents. And analogously, the children of I is all the nodes that have the receiving endpoint. Okay, so is it clear? So this is the set of parents and the set of children. Okay, so as we said during in the first lecture, each vertex of the graph represents a random variable. xi. And each edge I pointing to j encodes that xj depends on xi. And since we're going to be in this linear case, linear Gaussian graphical models, this dependence is going to be linear. So I'm going to tell you exactly how. But so the causal interpretation is, that there really is some cause from xi into xj. Xj somehow is being caused by xi. So usually we want to avoid some kind of causal loop. And so this means that usually G is taken to be a DAG. And what is a DAG? Well, a DAG means directed acyclic graph. So it means it has no directed cycles, right? So DAG, directed acyclic graph. Right, so that means we don't allow cycles, no cycles. A cycle would be something like a sequence like this. I1 pointing to I2, pointing to I3, and then at some point you have some I R, and then again I1. So then we don't allow something like this.
Undirected cycle or a loop? Undirected cycle?
Yes. So if I mean, all my edges are directed, but if I remove the direction, it's allowed.
No, a cycle with direction, but like this. Two edges are like this is
Yes,
also
this
it is a loop.
yeah. So for example, something like this is allowed, right? So it's a cycle, but it's not a directed cycle. So this is an example. I already have now our first example. DAG. Okay, so in particular, note that there will be no loops, right? So while a loop will be something like I pointing to I, right? So this is not allowed. Okay. So what is the model? Well, the idea is that each variable is a linear combination of its parents. But of course, since these are random variables, we don't expect this to be precise. So we allow for some noise. Okay, so up to some noise. And what does this mean exactly? Well, xi, let me write xj, is going to be the sum over all the parents of j. And I'm going to have the linear combination. So I'm going to have lambda ij xi plus some epsilon I, epsilon j. So this is going to be my equation. And so what is this? So lambda ij is going to be an edge coefficient. No, for the edge, right? For the edge ij. And this is measuring how strong is the influence from xi to xj, right? So this lambda ij is going to quantify, right? Is this a positive influence? Is it a negative influence, right? And how strong this is. So this is the lambda ij. And the epsilon, that's the error, right? So this is going to be independent noise variables. And now, well, one thing we're going to do is that for simplicity, the xj's are going to be centered, which means that we center our data by subtracting the mean, and then we're going to assume that all of them have been zero already. Right? So this is not a big assumption. So I'm just going to write here. So for simplicity, all xi's are centered. So that means that the expectation is zero. That's the idea. And so so that the expectation of this epsilon j are all zero. So we can take these errors to really be centered at zero. And well, we say the word there is Gaussian, right? So linear Gaussian graphical models. So the epsilons are going to be Gaussian, right? So since we are in a Gaussian setting, we're going to say that epsilon j is going to be a univariate Gaussian with mean zero and some variance omega j. Right? So this omega j is going to be the variance, and it's going to be positive for all j from 1 to n. All right, so I want to give you an example. So let's do an example of such a network, and what does these equations, what do they mean? So let's see. I'm going to have the following DAG. So this is my DAG, and I'm going to add the edge weights. So this is lambda 2, 3, lambda 2, 4, lambda 3, 4. Here, lambda 1, 4, lambda 4, 5, and lambda 1, 5. Okay, so this is my weighted DAG. Right, look that there are no directed cycles. Okay, so what is this model telling us? So I'm going to go in order from 1 to 5 and see what is this equation telling us. So the first one, x1, says, okay, my model is that x1 is a linear combination of the parents of x1 plus some error. But 1 has no parents, right? And so this means that it's only the error, right? So this is epsilon 1. Okay, so now I go to x2, and it's the same, right? No parents. And you can see it's a different error. Okay, now x3 now actually has a parent, right? So 2 is the parent of 3. So this means that this is going to be lambda 2, 3, x2 plus epsilon 3. Okay. Now x4. And so x4 has 2 parents, right? 2 and 3. So this is going to be lambda 2, 4, x2 plus lambda 3, 4, x3 plus epsilon 4. Oh, did I make a mistake?
Does it have 3 parents?
Oh, it has 1 parent more. Thank you. I was missing 1. That's correct. Very good. 1 is also a parent. Very good. So then this would be lambda 1,4 x1 plus epsilon 4. Great, yeah, that's true. So 4 actually has 3 parents. Then all of them should appear, indeed. And then x5 has only 2. x5 has only 2. And so then this will be lambda 1,5 x1 plus lambda 4,5 x4 plus epsilon 5. Okay, very good. So hope then everybody now agrees on this equation. And what I wanted to point out is that okay, so this is a nice way of having the equations, but maybe there is a compact way to rewrite this system with just matrix and vectors, right? Because if we look at this, if I just write x1, x2, x3, x4, x5 as a vector, we can rewrite this equation as here I can have a coefficient matrix and then put again x1 to x5. And then add just the vector of the epsilons. Okay, and so the question is, well, what is this matrix? Well, we can see, so for x1, you don't need any combination. So this was gonna have just a row of zeros. And for x2, this is the same, I think. And so now x3 actually has one non-zero entry, which is lambda 2, 3. So we're gonna have 0, lambda 2, 3, 0, 0, 0. Then the fourth row is the most interesting one because it has 3 non-zero entries. Sorry? Oh yeah, you're telling me what it is. Lambda 1, 4? Yes, lambda 1, 4. Yes. Yeah, okay, good. Yeah, yeah. Yeah, this is lambda 1, 4, then lambda 2, 4, and then lambda 3, 4. Right? And then 0, 0. And finally, well, lambda 1, 5 appears. And then we have a couple of zeros. And then lambda 4, 5 and 0. So this is the matrix, right? So if we name, so let lambda be the matrix. So it's going to be an m by m matrix. This already means matrix. It's a matrix such that lambda ij is what we expect. So this would be the weight lambda ij if there is an edge from I to j and 0 otherwise. Okay, so if we name this matrix lambda, then this, well, unfortunately, this is not lambda, right? Not that this is not lambda, but what is it? But I would have loved it if that were lambda, but you can see that it doesn't match, right? The entries are not in the ij. So, but this is very close to lambda, right? So what is it? Does anybody see it? Yes, transposed. So this is actually lambda transpose. Note that this is lambda transpose. So, okay, then let me erase. So when I'm claiming this is actually then a general statement, right? So so we can write X equals lambda transpose times X plus epsilon and well, I hope everything is clear what each one of these are, right? So X, of course, is the vector x1 to xm. Epsilon is the vector epsilon1, epsilon m. And lambda, I just defined in general. And so this is a nice equation. And note that X appears right in the left-hand side and the right-hand side. So maybe we can try to solve for X, right? So if I put everything on one side, I will get the identity minus lambda transpose times X equals epsilon. And we'll note that I minus lambda transpose is the same as I minus lambda transpose, right? By linearity of transpose. And so if identity minus lambda is invertible, if it's an invertible matrix, then we can actually solve for X in terms of lambda and epsilon. Then we would have that X equals identity minus lambda minus transpose times epsilon. Right? So here I'm using that, well, this matrix is going to be invertible if and only if the original I minus lambda is invertible, and then the inverse of the transpose is the transpose of the inverse, right? So then this looks like this. And so, well, this is going to be a question that we're going to address soon. But what I want to point out is that if I want to know, I mean, in the end, we want to study the distribution of X, right? And in particular, the covariance of X. And the good news is that what did we assume about epsilon? So what is the distribution of epsilon? Right, so epsilon is a random vector, right, of Gaussians. And they are all independent. So I claim if you put them together, you're going to get a Gaussian again, right? So this is going to be a multivariate Gaussian with what mean? Well, all of the means were 0. So this is the 0 vector. And what's the covariance matrix? Do you see it? So the covariance matrix, each epsilon has variance W or omega. I call it omega J. So this is going to be omega, where omega is a diagonal matrix with the omegas in the diagonal, and then everything else here. Right, so is this true? So you agree? So note that this is true. And so this is amazing news because what does that mean? What does that imply about X? Right, so epsilon, now it's a multivariate Gaussian vector. And now this is a invertible full rank matrix that is multiplying epsilon. So we just saw at the very beginning, I recall, that's why I did it. I recall that then this has to be Gaussian again. And we know exactly what are the parameters, right? So this means then that X will be a multivariate Gaussian and the mean is still going to be 0 as we want, and the covariance matrix. So remember the formula, it was A sigma A transpose. So this means identity minus lambda minus transpose times omega times identity minus lambda inverse. Right? That's the transpose of this. And so this is the punch line here, that our X can be completely determined from our parameters lambda and omega. We know now the covariance exactly of this Gaussian. And so, yeah, so this is really great. And then this actually gives me the definition of the model for sure. So definition, let G be a directed graph with m vertices, then the linear Gaussian graphical model associated to G is right. So a model, as I think Thomas also mentioned, a statistical model is just a set of probability distributions. And in this case, it's going to be Gaussian distributions. And the idea is, well, these are all the Gaussians that you can obtain for some choice of parameters, omega and lambda. So it's going to be the set of all multivariate Gaussians, 0 sigma, such that sigma belongs to the set mg, and mg, I'm going to this set RD, and RD reg is reg stands for regular. So this is just all lambdas in RD that are invertible. So I'm just gonna write the determinant of identity minus lambda is different from 0. Because we need this I minus lambda to be invertible. So I am only allowed to take lambdas in this set, RD reg. Right? Otherwise, I get an error. I cannot do this. Right? So this is, does this make sense? Right? So this is just the set of matrices that have zeros in the right places. That's whenever there is no edge, there is no cost from I to j. And then we have this RD reg, so that we can construct this covariance matrix. Okay. So let's I want to talk a little bit about what this assumption does. And the nice thing is that if you have a DAG, as I said, we usually consider this to be DAGs, then you don't need to worry about that. So let me tell you what I mean by this. So if G is a DAG, then there exists a so-called topological ordering of the vertices which, what does that mean? Topological ordering means that if I have an edge I to j, then this means that I is less than j in this ordering. So I will always have, when I draw the graph, I drew it in a way such that if I is pointing to j, when I order the label, the nodes, the node I comes before the node j. That's the definition of topological ordering. And if this is true, in this case, this lambda matrix, what kind of matrix is it? So if, remember, lambda is defined here, right? Lambda has entry lambda ij whenever I is pointing to j and 0 otherwise. So if this holds, what kind of matrix is lambda? It's a triangular matrix. Is it upper or lower triangular? Upper, right? So that means that lambda is an upper triangular matrix. And since there are no loops, there are actually zeros in the diagonal. So that means that when I compute identity minus lambda, this is going to be still upper triangular, and now it's going to have ones in the diagonal, right? So then the determinant of this is going to be 1, which is different from 0, right? So this means so that lambda is automatically invertible, right? So what I'm saying here is that if we have a DAG and we choose such an ordering, then that's a great question. I'm going to address that in a second. So if G is a DAG, then RD is the same as RD reg. So then we don't need to worry about this distinction about the reg and the D because they are always going to be the same. And yeah, there was a great question about, well, can we always actually, I claim this topological ordering exists. And in here as an example where it is, but okay, that's not a proof. So yes, it's actually, being a DAG is actually equivalent for this thing to exist, right? So to see the converse, it's easy because, if you have such a topological ordering, there cannot be a cycle, right? Because then you would be I less than J less than, and then less than I. That would be a contradiction, right? So a topological ordering implies that there cannot be cycles. But why the opposite is true? Well, I'm going to do something. I'm going to give you an algorithm to label them. And that's known. There are many algorithms, different complexities. Usually they're linear time. I'm going to give you Kant's algorithm from around 1962. So the input is a directed graph.
Sorry,
Yes.
You write it terminate of I minus lambda is no zero.
Yes.
So it implies lambda is automatically.
Oh, thanks. I that's not what I meant. Okay, I'll just write 1 minus lambda. Thank you. Yeah, what I meant is that lambda is automatically in RD reg. Yeah, thanks. So the input is a directed graph, DD. And then the output is a topological order. Labeling of P. And so I think just to save time, I'm not gonna write all the steps of the algorithm, but I'm gonna tell you what it is. So the algorithm is quite simple. So you have a graph. And so I'm gonna take as an example, maybe this graph. But you can take whichever one you like. And the algorithm is gonna say, look at the nodes that have no parents. So let's say you have, how is my graph there? Okay, like this. So the algorithm says, look at the nodes that have no parents. Choose whichever one you like and just label it 1. So here, for example, well, let's choose this one. Right, so look, I already have a different ordering than there. And then what you do is you remove all the edges to all of its children. So then I would remove this and I would remove this. And now I ask for each of the children, oh, are they now without parents? And if they are, then I add them to this list of without parents. So then I go again. Now, of the ones that are remaining, who has no parents, you can choose and just label it next. So in this case, maybe I'll label this 2. And if I do that, then I remove this edge. And now we're here. And then again, choose. And I say, okay, maybe I'm going to choose this one, 3. And then I remove. And I remove. And then again, there's one that's without parents. I choose it as 4. And then finally, this is the last one without parents. That's 5. So I end up with an ordering such that when you put the edges back, it's a topological ordering. Right? And you can see it's not unique because you have this choice on how you can do this. And let's say I try to do this on something that's not a DAG, maybe something like this. And I start the algorithm. I'll start, okay, who has no parents? Okay, this guy. 1. I remove. Then who has no parents? No one. Everybody has a parent. So then the algorithm says, but there are still edges. So then the algorithm says error, right? So it's like, no, not a DAG. Right? So the algorithm fails. Okay? So that would be the scans algorithm. And then you can use it. And maybe in the tutorial, I can have some graphs and then you can apply it yourself. Okay, so let's do an example to understand this MG. So let's do the first example that I gave you was 3 random variables that we're pointing to here, if you remember. So then we have lambda 1, 3, lambda 2, 3. So if we do MG, well, I need to know what lambda is. So first, what is lambda? Lambda has, now we know it's going to be upper triangular, right? So there's a lambda 1, 3 here and a lambda 2, 3 here. And so everything else is 0. And well, the cool thing is that if you do I minus lambda inverse, well, I minus lambda is going to have the 1s here and then I get minuses. And then you take the inverse. And well, normally inverses are messy, right? Like computing an inverse of a matrix. But in this case, it's so nice, right? That the inverse is just 1, 1, 1. And then just put the lambdas here. So that's the inverse of I minus lambda. And so if you think about it, it will not be surprising if you think about Gaussian elimination and how to invert this. You only need to do a couple of column operations that will bring you this back. Well, okay, you can also just check that I minus lambda is multiplied by this. It's going to give you the identity. And so this means that when I do MG, so where's my definition of MG? I guess I erased it already. But yeah, okay, you remember it. So it was I minus lambda inverse transpose. So I'm gonna have 0, 0, 0, 0, lambda 1, 3, lambda 2, 3, then omega 1, omega 2, omega 3. And then here this particular I minus lambda inverse. Okay, so then we can multiply. Well, okay, so this is such that omega 1, omega 2, and omega 3 are positive, right? That's the set NG. And the question is, okay, this is NG, but I want to maybe write it a bit more explicit. Oh, it's here. It was here. Great. So MG is this, which is what I just wrote. Right, so the lambdas here are arbitrary. I'll write them here, basically. Lambda 1, 3, lambda 2, 3 in R. And so, yeah, what happens if you multiply these three matrices? So, I mean, we could do it together, but maybe you can just see. It's not hard to see that this is going to be this. Is omega 1, 0, lambda 1, 3, omega 1. The second row is 0, omega 2, lambda 2, 3, omega 2. I mean, this is a symmetric matrix, right? So it has to be symmetric. So lambda 1, 3, omega 1, lambda 2, 3, omega 2. And the last entry is the most interesting one. It's lambda 1, 3 squared, omega 1, plus lambda 2, 3 squared, omega 2, plus omega 3. So this is it. And the same restriction as above. And so the first thing to note, if I think about this as a subset of PD3, right, the positive definite matrices 3 by 3, what are the restrictions really? If you think about the positive restrictions, if this is anything positive, and you can see that if you put kind of entries here, you're gonna be able to solve for parameters lambda 1, 3, lambda 2, 3, and here for omega 3 to find anything you want. The real restriction here is this should be catching your attention. Here, there are these zeros. And so that means that any sigma that lives in MG satisfies that sigma 1, 2 is 0. And we learned in the first lecture, what does that mean about the variables x1, x2, x3 if you have a Gaussian? What was it? Independence, right? So this means that x1 must be independent of x2 in this model. And remember, that's exactly what our intuition was telling us, right? That x1 is independent of x2. So now we see it from this equation. And this is, I say it algebraically because it is really algebraic equation, but it's an easy one. It's a linear equation, right? This is actually a linear space of symmetric matrices. So, so if we take, I'm gonna now start to move towards algebra because I I told myself that I was going to maybe connect now a bit more with the algebra. And so if we take the Zariski closure of this MG, right? Zariski closure in the space of symmetric matrices, then this is V of sigma 1, 2. So the vanishing set of just the equation sigma 1, 2. And so let me see. Okay, so it's a linear space of symmetric matrices. It's actually 5-dimensional, right? So in the space of symmetric matrices, this is a space of dimension 6, right? If you think about it, there are six coordinates, right? Sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 2, sigma 2, 3, and sigma 3, 3, right? These are just the same. And so this is a 6-dimensional space. And inside that space of symmetric matrices, I have one equation, which is sigma 1, 2 equals 0. And then this MG is a linear space of symmetric matrices when you think about this closure. And so in the last minutes, I'm going to give you one more example. What happens if I now consider this graph? Very simple graph too, just a path. 1 goes to 2, 2 goes to 3. Okay, then you can compute everything, right? So lambda is gonna be 0, lambda 1, 2, 0, 0, 0, lambda 2, 3, 0, 0, 0. You can compute I minus lambda inverse. Okay, maybe I'll leave this as an exercise. We can check it in the tutorial. I'm just gonna give you already what MG is. So MG is gonna look like this: omega 1, lambda 1, 2, omega 1, lambda 1, 2, lambda 1, 3, lambda 2, 3, omega 1. Then this is symmetric, so I'm not gonna bother writing it again. Here, lambda 1, 2 squared, omega 1 plus omega 2, symmetric. Lambda 1, 2 squared, lambda 2, 3, omega 1, plus lambda 2, 3, omega 2. And the last entry is lambda 1, 2 squared, lambda 2, 3 squared, omega 1, plus lambda 2, 3 squared, omega 2, plus omega 3. Okay, so it's a bigger matrix than expected, like this. And the same restrictions as before. So the lambdas can be anything, and the omegas have to be positive. And so now it's not so easy, right? So the question is, what is this set? We would expect this to be, again, 5-dimensional, if you think about it, because there are 5 parameters, 3 omegas and 2 lambdas. So in the space of this 6-dimensional space, we expect this to be 5-dimensional. And look at the wonder of everything here. These are all polynomials in lambdas and omegas. So the image is going to be a nice semi-algebraic set. And there is an algebraic variety associated to it, right? So if you take the closure, and the question is, what is this variety? Right? I expect it to be actually a hypersurface. What is the equation? That's the big question. What's the equation? So I'm going to tell you the equation by noting what happens if I multiply sigma 1, 2 times sigma 2, 3. So sigma 1, 2 is this. And sigma 2, 3 is lambda 1, 2 squared, lambda 2, 3, omega 1, plus lambda 2, 3, omega 2. Okay. And well, we can actually factor one of the lambda 2, 3s. So it's this lambda 1, 2, lambda 2, 3, omega 1 times lambda 1, 2 squared, omega 1 plus omega 2. But this is exactly sigma 1, 3. And this is exactly sigma 2, 2. So a miracle happened. And then this is, that means that the equation that we get is a binomial. Right? So this means that sigma 1, 2, sigma 2, 3 minus sigma 1, 3, sigma 2, 2 is 0. That's the equation. And then immediately you should start thinking Thomas. Right? So this binomial, so could it be that then the ideal associated to this variety, right, this mg, is going to be a toric ideal, right? So then there could this be, right, these connections now to the lecture from Thomas. And so the last thing I'm going to say is I'm going to define then the ideal of this graphical model. And so definition, so in this space of symmetric matrices, in the polynomial ring, the natural polynomial ring is going to have variables sigma. So K sigma, which is defined as K sigma ij, where 1 less than or equal to I less than or equal to j less than or equal to m, right? So the variables are going to be these sigma ij's. So in that polynomial ring, I'm going to define an ideal, and the ideal is going to be the vanishing ideal of mg, right? So we define ig to be the set of all polynomials. I was going to write C because usually I can go C, right? But okay, K sigma, such that if mg, when you evaluate it on mg, is 0. Right? So again, so what does this mean? So this means that when you evaluate this polynomial on something of the form I minus lambda minus transpose omega I minus lambda inverse, this will be 0, right? For all choices of lambda and omega in our definition of mg. And then, of course, then we will have this ideal, and the variety associated to this ideal is going to be the mg closure, right? This is the Zariski closure, as you learned in the preparatory lectures, right? In this correspondence between ideals and varieties. And so this is great because now we have for each graph, for each linear Gaussian graphical model, you can associate an ideal. And now the key question is going to be, how can we understand the properties of the model from understanding the ideals, right? And first of all, how can we compute this? Well, you learned this in the preparatory lectures. This is an implicitization problem because we have a parameterization. We have a nice rational, in this case, a polynomial parameterization, and we're trying to find the equations for the image. So it's an implicitization problem that can be solved with Grosvenor basis. And then that's how we would find equations like this. And then the task is going to be how to interpret, as Thomas was saying, like you can look at the output and say, okay, great. But what does this mean for statistics? What does this mean? Well, I'm going to already tell you the answer, and we'll see that next time, why this is true. This actually means that x1 is independent of x3 given x2. This equation will exactly mean this. And that will match the intuition we had there when 1 goes to 2, 2 goes to 3. If you condition on 2, then 1 and 3 become independent. Okay? So exciting things are coming. And I think I'll stop there. Yes.
We have a physical phenomena, we model it in the form of a differential equation, and we try to find the solution of that differential equation, either exact solution or we use numerical approaches. So my question is, what is the purpose of doing this whole procedure? Our particular goal is to target the solution. So what is the point of doing this whole procedure?
Okay.
Any drawback in that method that we are using this method now?
Okay, well, the point well, depends on who you ask, right? So if you ask the algebraists, then they want to study these ideals and understand them, right? But okay, if you ask the statisticians, I mean, what you want to do in the end is you observe data, right? You observe x's, and you want to, in the end, recover this graph. So what are the relationship between these variables, and how strong is the relationship, right? So we want to estimate not only the graph, but then we want to estimate the lambdas, and we want to estimate the omegas, right? So it's a hard problem if you want to do everything, right? But so the idea will be that from data, I can construct a graph, and I can find lambdas and omegas that are going to be a good fit to my data, and then I can do inference from this data, right? So remember we had this thing, I had this graph with like cancer and asbestos and smoking. We want to know, so like, okay, there's a smoking, there's cancer. Is it true that where is the edge, right? Is the smoking causing cancer, or is like cancer causes you to like want to smoke, right? So this is very important, right? In the end, this has the, ramifications in applications. I don't know.
This is a kind of a study of correlation.
Yes, exactly. We're understanding the covariances, right? The correlations between these models. It's very close to regression. I'm glad that you mentioned that, because this is actually, if you think about a node and look at its parents, this is linear regression. So it's a bunch of linear regressions put together. Yeah.
So are there any other questions?
Yes, Dr. Imran, yeah, there is a question from IPA side.
Okay, okay, go ahead.
Yeah, this is Adnan here. Can you listen me?
Yeah. Please go ahead.
Yeah. My question is actually when I initially look at your overall setup, like when you establish the links in terms of DAG, where you establish the links in terms of parent-child relationships. So I was just thinking, like, if we consider like the sequential model in terms of time series data, so it means that we can establish the parent-child relationships in terms of like lead and lag variables. So think in terms of vector autoregressive model. So I think your the system which you actually establish in terms of the causal relationships, here you introduce the direct variables and you establish the causal relationships. But when we consider the vector autoregressive, we can also establish in terms of sequential models, in terms of like in data sciences, we use that. So where we can think like the lag values as the parent and the current values as the child one. So I think the overall vector autoregressive model setup actually converges to your whole setup in that sense. And then later on you can find out the ideas and then and relate the final conclusion which you draw in terms of the I minus of this lambda. So I think that can be like converted to the time series settings and as well as to the cross-section settings. So at this moment you assume the cross-section settings, but we can also extend the similar framework in the time series settings.
My short answer is yes.
Yeah, this is a kind of a remark. I think.
The remark, yes.
Yeah. Thank you very much for.
Yeah, thanks for the remark.
Because this is really very important. Yes, sir.
These ideas are not necessarily binomial, right?
That is true. So that's one question, right? So are they, the two examples I gave were actually binomial, but I mean, yeah, this is a monomial ideal, and then this is a binomial. But then, is it true in general? So this will be actually, this is an open question to characterize the graphs that have a toric ideal. This is still open.
But in examples were kind of orthogonal graphs or triangulated graphs. At least for these kind of graphs, is it true or?
I mean, we'll understand this a bit better.
Or in general, I mean, does such kind of graphs make the life easier in your literature somehow?
Well, yeah, the answer is yes. Yeah, choral graphs are very nice for sure, and they will make things easier. We'll see in the tutorial. I'm gonna have a cycle like this. This one is not toric anymore, and because there will be some higher degree equation coming up, a cubic will appear, and quartic even, because I have 4 variables now. So yeah.
Okay, are there any comments or questions? Yeah. Okay, if this is the case, let us thank Carlos. As announced earlier, we have a short ceremony here, so I will keep you. I request you to please stay in this room so that we can have this linear distribution ceremony right here, right now, because maybe we will be one of the speaker will be in Karachi from next year. Okay.